But I wanted to start today with the talk by Bernd Sturmfels from UC Berkeley and MPI Leipzig. And he will talk about, I cannot see the title there, algebraic statistics with a view towards physics. Yes, please.
Yeah, thank you very, very much for the invitation. So, of course, I'm from the math side and a little bit of a different background than some of the others. So I like to tell you my perspective, how I got to some of the themes that are discussed here. And of course, in statistics and physics, we both like graphs, as seen here. So let's start with a discrete statistical model. So by this, I simply mean a subset of the simplex, the n-dimensional simplex of non-negative real vectors with n+1 coordinates that sum to 1. So a data set is summarized in an empirical distribution at some point with rational coordinates in that simplex, and ui is the fraction of samples that were observed to be in state I. So that's going to be our data. So in maximum likelihood inference, we are trying to find the point in the model that best explains the data in the likelihood sense. So the maximum likelihood estimator of some model M is the retraction from the simplex onto the model, the map from the open simplex onto the model, where the image p hat is the maximizer of the log likelihood function. So the log likelihood function is the linear combination of the logarithms of the pi, so there's the unknown positive probabilities, and then the coefficients ui are the data. So this is the function we seek to maximize, and if there's unique maximizer, we call it p hat, and that's the maximum likelihood estimate for the given data with respect to the model. Now, in algebraic statistics, these models are usually described by polynomial equations. So they are the positive points on some variety. So if M is such a variety, then phi is an algebraic function. That is to say, its graph is a semi-algebraic set. And the algebraic degree of this function is called the maximum likelihood degree, or ML degree of the model. So the ML degree is the number of complex critical points for generic data vector U, and that's an intrinsic invariant of any algebraic discrete statistical model. So here's a cartoon that's from a book called Algebraic Statistics in Computational Biology. So B stands for biology. And here's a cartoon. So this triangle represents the probability simplex. The red wiggle is our model. We have some data point, U, that's the empirical distribution, and we seek to find the closest point in the likelihood sense to the data that lies in the model. Often the model is given in parametric form, so there's a low-dimensional parameter space of which the model is the image under some map F, and we can ask either for the maximum likelihood distribution, p hat, or for the maximum likelihood parameters. And in ideal situations, this will be one-to-one or locally one-to-one or identifiable, as statisticians would say. That's the geometric picture to keep in mind. Now here's the first honest picture. And this is the model of independence for two binary random variables. So here in this example, n is 3. So the simplex is the tetrahedron, and the independence model is this quadratic surface that's shown. It's a surface inside the tetrahedron. So let's say you have two binary random variables. So let's pretend gender were binary. So they're males and females. And then let's say main interest, mathematics or physics. And we're interested in the question whether there is independence between gender and field of preference, or whether there's a correlation, positive or negative. Well, to answer that question, we collect data. So the data is a non-negative integer matrix U, where these four integers record respectively the number of male physicists, male mathematicians, female physicists, and female mathematicians. So we organize that into a 2x2 data. And then to be independent means that this matrix has rank 1. So perfect independence would say rank 1, that means we're on the surface. And then if we're on one side or the other, there would be a positive or negative correlation. The sum of the entries is called the sample size. The empirical distribution is obtained from the sample by dividing by the sample size. And in this case, it's very easy to write down the maximum likelihood estimator. It's a rational function in the data. So we teach this to freshman biologists at UC Berkeley. This is obtained. You calculate this by taking the row sums, you multiply the row sums by the column sums, and then you divide by the square of the sample size, and this gives you the maximum likelihood estimator. So there's a map from the tetrahedron onto the model, onto the rank 1 tables, and this is the formula. What I want you to notice about this formula is this is a alternating product of linear forms with positive coefficients. So this tetrahedron and the surface that you see is very much positive, very much a positive geometry. Let's do another example, very simple example. Let's perform the following experiment with a biased coin. You flip the biased coin. If it shows heads, you flip it one more time. So there are 3 possible outcomes. Either there's heads, heads, or heads, tails, or just tails, right? So I'm going to write P0, P1, and P2 for the probabilities of these 3 outcomes. They form a triangle, delta 2. And then the model is a curve in that triangle. So the model parameters, so S0 is the bias of the coin, the probability that heads comes up. And then, of course, tails is 1 minus S0, which I denote by S1. So then in parametric form, this is the parametrization of the curve. So 3 probabilities are S0 squared, S0, S1, and finally S1 for tails. And these things sum up to 1. The implicit representation as a quadratic curve, projective variety intersected with our triangle. This is the implicit equation. And now you perform experiments. So you do this experiment 1,000 times and you record the outcome in the data vector or the empirical fraction. Again, there is a nice formula for the maximum likelihood estimator. Namely, what you do is you count the total number of dice, the total number of coin flips. So the total number of coin flips is 2U0 plus 2U1 plus U2. And then you look at the fraction of heads. The fraction of heads is this numerator, 2U0 plus U1. And then the other expression here is the fraction of tails, and that are the maximum likelihood parameters. We're more interested in the actual model and describing the contraction onto the curves. You plug in the maximum likelihood parameters into this formula, and you get this expression for the maximum likelihood estimate. So this is a map from the triangle onto the curve. And again, I like to emphasize that this is an alternating product of positive linear forms. That is to say, linear forms whose coefficients are positive integers. Now, how often does this happen, that the maximum likelihood estimator is rational? How can it be rational? Well, let's start with an analogy. Let's suppose, rather than doing likelihood inference, we just pick the nearest point map in the Euclidean or high school metric. So suppose M is a real variety in R to the n, maybe compact. And let's write phi for the nearest point map in the Euclidean metric. So for every point in R to the n, we map to the point in the model, in the variety that's closest. Now, then I claim that phi is a rational function if and only if is a linear space, right? The if direction you know from analytic geometry, from high school or undergrad days, but the only if holds true as well. So the question is, if we now replace Euclidean metric by the statistically meaningful Kullback-Leibler divergence that describes likelihood inference, what plays the role of linear spaces? Okay, so the role of the nearest point map is now played by the MLE, and the question is which models play the role of linear spaces, which have ML degree 1. Okay, so then, well, we saw in these formulas how this goes, and there's a general theorem to this effect. So this was solved by Junha in a paper called Varieties of Maximum Likelihood Degree 1. So this is scenarios under which this map is a rational function. And this was a sort of a complex algebraic result. And then we transferred it to the positive semi-algebraic setting that was actually relevant in statistics in this more recent paper called Discrete Statistical Models with Maximum Rational Maximum Likely Estimator. And the theorem basically said what you see in these examples. It's always, the function is always given as a product of alternating product of linear forms with positive coefficients, making the positivity of the geometry evident. Now, the setting we like to couch this in algebraic statistics has been, for the most part, using projective variety. So we saw with my coin flip example that I wrote a homogeneous quadratic polynomial in 3 probabilities. So let's generalize this. So we work in a projective space, complex projective space with coordinates p0, p1 up to pn. Say m is a projective variety. We collect data. Let's say that's an integer vector u of length n plus 1. And then the likelihood function is a rational function on projective space that we restrict to the variety. So it's simply given, this is the product, p0 to the u0 up to pn to the un. So this is the monomial or Laurent monomial given by u. But then to make it homogeneous of degree 0, we have to divide by the sum of the p's raised to the sample size. Now, of course, in the statistical application, this will be 1. So this plays the role of the hyperplanar infinity. But the way I've written it here, this is a well-defined rational function on projective space and hence on the variety. Now notice that n plus 1 hyperplanes occur in this formula, right? So the coordinates pi and the sum of the pi. So let me write h for the arrangement of n plus 1 hyperplanes that you see in this formula. So this theorem sums up basic facts about the situation. So the number of complex critical points of this likelihood function is independent of u, provided u is generic outside a codimension 1 hypersurface. This is the ML degree of the model as defined earlier, and it equals the signed Euler characteristic of the variety minus the n plus 1 hyperplanes, provided that complement, that difference is a smooth, very affine variety. Very affine means subvariety of the torus. Now, in the physical situation we want to get to, these varieties will be smooth. So this will be true that ML degree equals the Euler characteristic. On the other hand, in statistics, often these models have singularities. And there we have to replace the Euler characteristic by a different topological invariant, another characteristic class known as the Chern-Schwarz-McPherson class. But you should think about the CSM class as a version of the Euler characteristic in the presence of singularities. But today I'll mostly talk about the smooth case, and here are a bunch of references. So the ML degree was first defined with Catanese and collaborators in 2006. And I mentioned Junha has worked on this, and it's an active area of research that researchers both in algebraic statistics and singularity theory work on. For example, here in this paper, ML degree calculations are used to obtain topological invariants. Now, how do you compute the ML degree? Well, let's suppose for a moment M is a linear space. So suppose M is cut out by homogeneous linear polynomials. Then there's a theorem, well known in our community as Varchenko's theorem, that says the ML degree is equal to the number of bounded regions in the hyperplane arrangement, right? So I have my linear space, say of dimension D. I intersect it with this hyperplane arrangement where I've taken my special hyperplane at infinity. So this will be an arrangement of n+1 hyperplanes in affine d-dimensional space, and then the bounded regions count the number of critical points. Moreover, if the data are positive, which they are in statistics, every complex solution is real, and there's one per bounded region. Now, this relates to a lot of nice combinatorics. A couple keywords are matroids, the characteristic polynomial, and Zaslavsky's theorem that has made its connection to this community. I want to advertise a recent work by Taylor Brysiewicz, Holger Ebel, and Lukas Kühne, who wrote an amazingly fast piece of code in Julia that just came out for computing the characteristic polynomial, hence the number of chambers. Now, what if the model is not linear? The world is generally not linear. That's why we are called the nonlinear algebra group in Leipzig. How would you compute the critical points in that case? Well, in that case, we have to use numerical methods from nonlinear algebra rather than linear algebra, and in particular, numerical methods relying on homotopy continuation are very popular these days. So there's a Julia package called homotopy continuation that I strongly recommend. It provides numerical solutions for systems of polynomial equations. And most importantly, it has a certification feature. So it has now a built-in feature that can certify the correctness of your numerical solution using interval arithmetic. So with a little bit of extra cost, you solve a system and you get a proof that the solutions that you found are correct and sometimes complete. And then I like to also advertise the book on nonlinear algebra. Now I'm going to end this whirlwind tour of algebraic statistics by posing the inverse question. And I'd like you to keep this in mind as we transition towards the particle physics models. And the inverse question is, given a distribution in the model, which data vectors have the given distribution as its MLE, right? So far, in the last 19 minutes, we said, let's start with data. We have a data vector U. Let's find the p hat that's in the model that best explains the data. Now let's turn this around, right? I'm fixing the maximum likelihood estimate, and I ask which data vectors could have led for it. So the set of such U is what we call the logarithmic Voronoi cell of the model at the point. Okay, so this logarithmic Voronoi cell is a convex body of complementary dimension, n minus dimension of the simplex. So it's inside the simplex. So the dimension of the simplex minus the dimension of the model. And it lies in the logarithmic normal space. So this is familiar in the Euclidean case. So in the Euclidean case, there will be the usual normal bundle, and then the normal spaces contain the Voronoi cells. But here we have this logarithmic structure, and these convex bodies were studied in a recent paper by Julia Alexander and Alex Heaton, and again, to compute them, ideally certified, you use numerical methods, homotopy continuation. So as we embark on the scattering models, you could maybe keep both this inverse question and June Herr's ML degree 1 characterization in the back of your mind. Okay, are there any questions at this point? Thomas, you will interrupt me if there's a question, maybe in the chat.
Yes, if there is something in the chat, I'll tell you. Yeah.
Very good. So now let's move on to some things that are probably more familiar to some of you. So this is the CHY model, and then its generalization, the CEGM model. The references are down here. These are leading to scattering equations. And this was discussed, for example, yesterday afternoon in Nick Early's lecture. Let's start out with CHY, and let's discuss 6 particles that travel on a line. So this is modeled by the moduli space M06. So M06 is the moduli space of 6 distinct labeled points on the projective line or Riemann sphere. And this is a three-dimensional space because we're working modulo projective self-maps of P1. Now, a convenient way to think about this open, non-compact variety is to take the Grassmannian G26. So open means I take the points on this Grassmannian, on this 8-dimensional Grassmannian, where all Plücker coordinates are non-zero, all 15 of them. Then I have a 6-dimensional torus acting naturally with the 1-dimensional stabilizer. And then this quotient is a very affine variety of dimension 8 minus 5, which is 3. Now, this embeds, for example, into a P8 by the non-constant 2x2 minors of a matrix like this. So this is called the gauge in the physics literature. So I pick 3 of the, so I write down a 2x6 matrix. I choose 3 points. I fix them.
So
and then I have 3.
There's a question in the chat. If you can explain once more what is very affine. What does very affine mean? Very affine means it's a subvariety of a torus of some C star to the n for some large n. So a projective variety is a closed subvariety of a projective space. An affine variety is a closed subvariety of an affine space. And a very affine variety is a closed subvariety of an algebraic torus. That is to say, the zero set of a collection of Laurent polynomials. So I have to take this space and now write it as such. And the way I'm going to do it as we did in statistics. Namely, I'm going to embed it inside a projective space. And then I rip out dimension plus 2 more hyperplanes from that projective space. So in this example, I do this as follows. So I take this 2x6 matrix. I have 3 free parameters for 3 traveling points. And then of those 15 2x2 minors of the 15 Plücker coordinates, 6 are plus or minus 1, and the other 9 are given here. And just for good measure, I'm going to scale them by 3s and 9s so that they sum to 1. Right? So this is honest to goodness. This scaling doesn't matter. I just wanted to fit exactly the framework that I had before of a statistical situation. So those are the 9. I interpret these 9 quantities as probabilities that sum to 1. So now the log likelihood function is the scattering potential, right? So given data uij, so given measurements for those 9 states, we seek the critical points of the log likelihood function. So this is the potential in the CHY models. Its derivatives are the scattering equations, and what we interpreted, we saw as data and statistics are the Mandelstam invariants. And the Mandelstam invariants here can be anything. If I use them on the whole, 15 Plücker coordinates, then there's some linear relations that are supposed to be satisfied. But the way I set it up here, I can pick any 9 numbers uij. So this is my problem. Well, how do we compute these critical points? Well, we solve this numerically, say, so the joy of numerics. So for certain positive integers, we find that the 6 complex critical points are all real, here given in floating point approximation. Notice that these 6 solutions exhibit the 6 permutations of 1 up to 3. So here's an increasing ordering in the second, then different ordering. So the 6 possible relative orderings are seen in the 6 solutions. The first solution would give the MLE in the statistics model, meaning the probability is actually positive and sum to 1. And confirming Varchenko, we see that all 6 solutions are real. And the bounded regions here are the 6 tetrahedra that triangulate the 3 cube, where the values of the x's are between 0 and 1. Okay, but this is familiar to this audience, and in particular, this was discussed by Nick yesterday. Now, in general, so the CHY scattering model for us would be a linear statistical model. So the moduli space M0M is a very affine variety of dimension M minus 3. So it embeds in a torus.
Just like before, we're writing a 2 by M matrix with the M minus 3 parameters called the gauge in the physics literature. The number of non-constant 2 by 2 minors is M times M minus 3 over 2. So this would be the number of states, N plus 1 in the statistics interpretation. And the Mandelstam invariants serve as the data. The CHY scattering equations characterize the critical points of this log likelihood function, and the ML degree is M minus 3 factorial. And for positive data U, all critical points are real. Now, we start out with this. We wrote a paper back in December with Simon Thelen, and we played around and computed these solutions numerically. So we took this kind of computation quite a bit further. And we noticed that we knew that homotopy continuation is very efficient, but it did particularly well on this class of computation. So here is M, 10, 11, 12, 13. This is the number of states. So the corresponding N plus 1 coming from this equation ranges between 35 and 65. The number of critical points, the number of bounded chambers here from 5,040 to 3.6 million. And then these three columns are timings measured in seconds. And I should explain this. So the first time is I choose complex data and I calculate the critical points in a first run for the complex data. Then once I have the full set of critical points reliably for well-conditioned complex data, I can then track them to the desired real point. That goes much faster. So for example, here, 2,000 seconds, then only 500 to trace to real. And then finally, there's a certification step, which I said, if you click an extra button, you say certify, the program produces an interval arithmetic proof that the 3.6 million numerical solutions that were found are actually correct. So this worked very nicely on this class of equations. Maybe just a minute or two, or homotopy continuation works. So there's an online phase and an offline phase. So the offline phase, in principle, you do once per model, once per statistical model, once per physical model. You compute all critical points for some data vector U that you choose. So this is done using a technique called monodromy loops. So here the base of this is a slice of data space U. Then over it, you have a certain number of critical points. You loop around, and exploiting the monodromy, you pick up more and more solutions as you loop around. And eventually, you will no longer pick up solutions. You have a first full set of solutions. Now, in the online phase, when the actual data come in, after you've asked 1,000 people about their gender and their preference among physics and math, after you collected data, and the new data vector is U prime, so then you compute solutions for the data vector U prime from the known solutions for U, and then afterwards it's certified. So here is the reference. So Julia, homotopy continuation was developed by Breiding and Sascha Timme. This is the paper about the certification. And this is the little article I wrote with Simon, where we discussed the connection between likelihood equations and scattering amplitudes. Okay, so points traveling on a line. The CHY model is relatively well understood, but in higher dimensions, things get more difficult. Let's define the moduli space for M points, labeled points, in general position and projective k-1 space. So in general position means no k of them on a hyperplane. And just as before, this can be conveniently written as the open Grassmannian. So this is the Grassmannian of k-dimensional vector subspaces in an m-dimensional space. So here k is less than m. Circle means we take the open part where all m choose k Plucker coordinates are non-zero, and then we mod out by the natural torus action. This again is a very affine variety. We can embed it into some torus. and it's smooth, so no need to deviate from the Euler characteristic. So it's smooth, and it has this dimension, k minus 1 times m minus k minus 1. So if k is 2, then this is the familiar m minus 3 from 5 minutes ago. Now, this being smooth, the Euler characteristic of this space, of this manifold, is the ML degree of the CEGM model. So the number of critical points of the likelihood function of the potential is equal to the Euler characteristic of this space. Now, already k equals 3 is a very interesting and challenging case. So this is the moduli space of m labeled points and P2, no 3 collinear. That's a 2m minus 8 dimensional space. Again, a little table. So if the number of points ranges between 6 and 9, the dimension or the ambient dimension, if we embed this into a torus, ranges between 14 and 75. So these are the numbers of non-constant Plücker coordinates. These are the known values for the maximum likelihood degree. So it starts with 26. This first got me hooked when I saw a paper by Freddie and Nick and collaborators. I saw the number 26 that got me hooked. And then I learned it goes to 1272, 188,000. And then for 9 points, it's already 74 million. Now, the first 3 we verified using the same methodology in the paper back with the Simon. And again, it was relatively fast. So the 188,000 takes about 70 minutes to find the complex solutions. And then the certification step is even faster. So it's in a range of 2 minutes. Now, these blue numbers are very, very interesting. So these ML degrees were known thanks to Freddie and collaborators. And in particular, in my view, the hero here is Thomas Lamb. So Thomas used matroid theory and the finite field computations, the connections coming from the Bay conjectures, to predict these numbers. So if you know the number of points over several finite fields in the appropriate realization spaces, the number of realizations of the uniform matroid, then using some magic combinatorics, you can predict these numbers, and this is exactly what Thomas did. In particular, the last number is very impressive, and I will return to this on the last slide of this talk. So we were not able to do this back in December. We ended at m equals 8. Now, there are many questions. For example, can all the critical points be real? And what about larger k and m? Right? How does this continue? Now, even here, this is very tantalizing. So we don't have a fully real set yet. We're short by 16. So we have an instance with 1256 real points, but we're still short. So we don't know yet, even this one. Now, let me digress a little bit and tie this in with the amplitudes. So here's the formula that many of you know, that you've seen on Nick's paper. So the amplitudes for the CEGM model, for example, are rational functions in the data, and they can be evaluated either combinatorially, using the beautiful combinatorics that Nick spoke about, for example, or numerically by summing residues over all critical points of the likelihood function. So here is the example for the 6 points on the line. So this is a rational function that's the sum of 14, that is to say Catalan many, 14 reciprocals of products. These 14 correspond to the 14 triangulations. Here's the associahedron. And the U's are the data, the Mandelstam invariance. So the U's with 3 indices, so U1, 2, 3, is a shorthand for U1, I believe, for U12 minus U13 plus U23. Okay, so there's an explicit rational function in terms of the data, the Mandelstam invariance. So Sima and I, since we had lists of these critical points, we did some numerical computations, and we were able to find these, right? So if the user integers, this is a rational number. It's fun to check this out. So based on system solving, we did a number of computations, and this inspired us to actually read the papers by Nima and Thomas and collaborators on positive geometries and canonical forms. I must say they're not so easy to read, partly because they're long. So you guys write really long papers, but we took up the challenge and read them. And we then used this to transfer a little bit of this to the statistical setting. So we talked about positive statistical models and their amplitudes. And I'll show you an example. And I do not completely understand this yet. So, but positive statistical models conclude all toric models. So statisticians call these exponential families, linear models like the one we saw, and all models of ML degree 1, the one we saw at the beginning. Now, why could amplitudes be interesting? Well, in a statistical context, well, likelihood inference is really frequentist statistics, but there's another camp. Those are the Bayesian statisticians. And the Bayesian statistician will not maximize the likelihood function, but he or she will integrate the likelihood function. So for example, here's the likelihood function, again, of some parametric model, and the exponents u0 up to un are the data. Now in Bayesian statistics, we're integrating over the parameter space against some measure, and that measure is the prior belief. So we have some prior belief, how the data are distributed, then we collect data, and then we update our prior belief based on such kind of calculation. So we have a parameterized model, and this is the kind of integrals that you might like to evaluate in Bayesian statistics. Now the amplitude is a certain limit of a certain transformation of this integral, and so here we formulate this as a theorem. Again, this is as a really corollary to the work of Nima, Thomas, and collaborators. So the amplitude of a positive statistical model is a rational function of the data. It equals the volume of the appropriate dual polytope. And then in the numerical setting, you can compute it by adding up the reciprocal determinants of the toric Hessian. So the toric Hessian is not the usual Hessian of the likelihood function, but you replace the usual derivative by the Euler operator. So rather than doing a derivative dxi, you do xi di. Now, this also relates, by the way, to moment varieties of continuous distributions. So there's very nice recent work of Cutley and Cohn and collaborators on moment varieties and Wex-Press coordinates, and that's another strand that connects algebraic statistics and amplitudes that I have no time to get into. Let's go back to males and females and physicists and mathematicians. So here's the independence model for the Segre surface, the 2x2 determinant, P1 times P1 sitting in P3. The relevant polytope is the square scaled by the sample size. You translate to put the origin in the middle, you dualize, you measure the area, and then you get this rational function of degree -2 minus the dimension of the square. And this is the amplitude of the independence model. So I have to say, I do not completely understand yet what the amplitude means in what it might mean for Bayesian statistics. And I would love to hear your thoughts on this. Okay? Well, this is the amplitude of independence for 2 binary random variables, the amplitude of the model depicted in this tetrahedron. Now, in the last 17 minutes, I like to slow down a little bit and talk about a project that we're currently working on at MPI in Leipzig. And this is a group, so Daniele is a researcher, group leader, Taylor, Lucas, and Simon are postdocs, and Claudia is a graduate student. And the working title we have for this is likelihood degeneration. So this is work in progress, and I'd like to tell you a little bit about this work in progress. So what we're now going to do is we're going to replace the data by new data that have a small deformation parameter t. So we're now going to work over the field of real Puiseux series. So Puiseux series are formal power series in an unknown t with rational exponents that have a common denominator. Now this is a very nice field. It's both an ordered field, right? Think of t as an infinitesimally small positive quantity. So it's both an ordered field and as a valued field, as a valuation. So the valuation of a scalar in this field is the smallest exponent of t that you see. It's a valued field. So in English, we introduce a small positive parameter. This is a real closed field. So it's an ordered field that has index 2 in its algebraic closure. The algebraic closure are the complex Puiseux series. So Puiseux series with complex coefficients, and that's a standard algebraically closed field used in tropical geometry. So now the data are not real numbers, but they have coordinates in this real closed field. So the ith data point, so ui, what we think of as the number of times, the fraction of times we made the ith observation, is now a scalar in this field. So it's alpha I t to the wi plus higher order terms in t. So alpha I is a non-zero real number. Wi is a rational number, and that is the valuation of ui. Now then we solve the likelihood equations. We get 6 solutions or 74 million solutions. Now, each of these critical points p hat have coordinates in the algebraic closure. So let's say the jth coordinate, the estimated probability or the jth state, is a complex number, beta j times t to the qj, qj a rational number again plus higher order terms in t. We can now ask the question whether we can go directly from the rational numbers wi to the rational numbers qj. Let's call this the tropical MLE problem. So given the tropical data vector, by which I mean these exponents, the vector of exponents, w, the rates at which the data move, can we directly compute the tropical critical points? So tropical critical point is the vector of exponents in the solution. So is there a formula that lets us write q somehow as a tropical algebraic function in terms of w? Here's a book reference for tropical geometry. We will see that this will be possible in some circumstances. Well, let me first give a very simple example and make a remark about the relationship between numerical mathematics and tropical mathematics. The relationship is a very happy one. There's happiness in both directions. I'm going to explain this by a simple example. So suppose we have this quintic equation of degree 5 in one unknown x. And the coefficients on our field, right? So t is among the coefficients. So we want to solve this for x. Now, of course, in high school, you learn the quadratic formula that I can never remember, or the cubic and possibly the quartic formula. But we cannot do this in radicals for this equation, thanks to Galois theory. And we can certainly write down series solutions. So you go to a computer algebra system, Sage, Maple, Mathematica, you type in Puiseux series, and you get the first few terms of the classical roots, and here they are. So there are 3 solutions that have order 0, this one, this one, this one. There's one solution that is linear in t, lowest term is as order 1. And finally, there's one solution of order 3 that starts like this, 7t cubed plus 982 to the 5th, and so on. Okay, so asymptotically, I have 3 solutions of the order t to the 0. Freddie and Nick would call this regular solutions. And I have 2 solutions of the orders t to the 1 and t cubed. Nick and Freddie would call those singular solutions. So tropical solutions are 0, 0, 0, 1, and 3. Okay. Now happiness holds both ways. Tropical geometry can make numerical people happy, and numerical mathematics can make tropical people happy. So first, from t to n, well, what you can do in a case like this, you can try to first find the tropical solution. So in this example, that's very easy. A technique known to number theorists and many others. You draw the Newton polygon, you read off the slopes, and then by a combinatorial analysis, you first find the tropical solution. You stare at the equations, you stare at the combinatorics of the equation, you read off 0, 0, 0, 1, 3, and then you use this tropical information, this combinatorial information, to build a homotopy for numerical solving. So you pre-process with tropical combinatorics, and you use that to build a numerical algorithm for tracking. But it works the other way around, right? There's also from n to t. So suppose this is not one simple equation. Suppose this is a very large system, and suppose we have no access to the combinatorial information. We cannot get the combinatorial information. But suppose we can solve numerically. Well, then we can use numerical tools, such as the monodromy loops I described, to solve the equations for smaller and smaller values of t. So let's pretend for a moment we can solve this for t 10 to the minus 3, 10 to the minus 4, and so on. Now then, from the resulting numerical data of floating point approximation over C, hopefully certified, you can learn the tropical solutions. So this is what I mean by happiness both ways. And we use both directions in our current study of maximum likelihood and scattering equations. Let me state a theorem which we have about linear models. Recall, linear models includes the CHY model, moduli space M0. So suppose X is a linear subspace of projective n space, interpreted as a statistical model. And let me write X perp for the orthogonal complement. So X is represent this as a real linear subspace in R to the n plus 1, and take the orthogonal complement with respect to the dot product and interpret this again in projective space. Now, both linear spaces can be tropicalized. So we can look at the corresponding tropical linear spaces. These are also known as Bergman fans. So this brings us back to the beautiful combinatorics of matroids and tropicalizations thereof. So here's a tropical plane in 3 space. Here's a tropical cycle space, the space of trees. So it's actually a rendition of the Peterson graph. We're going to talk about NBC bases in a moment. So there's lots of combinatorics. So tropical linear spaces are pretty much matroids and very well understood combinatorial. So here's one theorem about tropical maximum likelihood. So suppose we have such a linear model and the tropical data vector W is sufficiently generic, then we can compute the ML degree in the tropical solutions by forming the following intersections. We take the tropicalization of the linear space X. We also look at the tropicalization of the orthogonal complement. We negate this and subtract it from the data vector. So we shift the dual, the negated dual Bergman fan, we shift it by the tropical data vector. So now this is a piecewise linear, this is a fan, this is a shifted fan. These two things have complementary dimension, they intersect in finally many points, and the number of points is the ML degrees, the number of bounded regions. So for example, if X is a completely generic linear space, then the number of critical points or bounded regions is n choose d, and we can write them explicitly as follows. We assume that W0 is the smallest coordinate, and I'm going to write En plus 1 for the all minus for the all 1 vector. So I form this expression, and here I take the sum WI, but I only sum over all indices I over some specified D element subset in 1 up to n. So the n choose D of these tropical critical points. It gets a little bit more interesting for special matroids. So let's discuss this for the CHY model. So let's go back to 6 particles on a line, and let's go back to the joy of numerics, which is also the joy of tropical geometry. So the CHY model, M06, is a 3-dimensional linear space in P8, where I set this up. This corresponds to an affine arrangement of 9 planes in R3 with 6 bounded regions. These are tetrahedra in a triangulated group. Let me choose my Mandelstam invariants to be these powers of t to the 12, t to the 6, up to t cubed. So this is the tropical data. So the exponents here is the tropical data vector or tropical Mandelstam invariant. So I'm going to apply this theorem, and I found that there are 6 tropical critical points, just like we had 6 classical tropical points before, and these are the 6 points. Right? So there is a map, takes these numbers to these vectors. And there are different ways to think about it, right? So think about them as specifying small arcs parametrized by t approaching 0, each of which lies in one of the 6 tetrahedra, and each small arc converges at the given rates to vertices of the arrangement. So again, for classical solution, I have 6 bounded regions, and each of them contains 1 critical point. But now with the t, the critical point moves towards a vertex of that bounded region. That vertex is chosen to be an NBC basis. And according to the previous theorem, each solution is a decomposition. I take the data vector and I decompose it as q hat, the tropical solution, and a dual solution, W minus q hat, whose sum ends are compatible with circuits and co-circuits of K5. Right? So this is gives a decomposition. This is compatibility with circuits in the complete graph. This is compatibility with co-circuits. Let's see one example. And so this is the example. So I call this slide tropical CHY scattering. So I take any vector, tropical data vector, and I write it as a sum of my tropical MLE and the rest of it, where these are respectively compatible to lie in the Bergman family. So here in this green picture is the complete graph K5. There's a distinguished edge. This comes from the setup that has weight 0. Every other edge so has an integer labeled to it. And then I contract this distinguished edge. Afterwards, I get a planar graph with 9 green edges. In blue, I have the planar dual graph. So the green circuits correspond to co-circuits in blue and vice versa. And what I've done here is I've written one of the 6 solutions as the additive decomposition. So you can see these labelings of the green graph have minimum is attained twice along each circuit. That's what it means to be in the tropical linear space. So if you follow any cycle here, 0, 0, 2, minimum is attained twice. 5, 7, 5, minimum is attained twice. Same over here in the complementary decomposition, you go 1, 5, 1, 5, and so on, minimum is attained twice. So both the labeling of the green graph has minimum attained twice on every circuit, and the labeling of the blue graph has this, and they add up to the data, and they're precisely 6 solutions, and this is the number of bounded regions, the Euler characteristic, or the characteristic polynomial evaluated one. Now, a very special case of this is the theory of soft limits from CUZ. So this model, XKM, the CEGM model, was studied with a degeneration technique that Kajafredi and collaborators called soft limits. So this amounts to performing tropical MLE with the tropical Mandelstam invariants given in a very simple 0-1 fashion. Namely, we focus on the last particle labeled M. And then for an IK set, we're going to set Wi to be 1 if the last particle appears, 0 if it doesn't appear. And in their paper, solutions are called regular if they tropicalize to the all zero vector, and singular otherwise. Now, regular solutions arise from generic fibers of the deletion map. So the deletion map that drops the last particle has the generic fibers or discriminantal hyperplane arrangements. So FKM is the generic discriminantal hyperplane arrangements. You take M points in affine K-1 space, completely general. You look at the hyperplanes they span. You take one of these hyperplanes and call it the hyperplane infinity, and then you count the bounded region. So that's the Euler characteristic of the fibers. Singular solutions are more subtle, and they are special. And we studied all of this using the numerical tropical happiness. But let me state one more theorem about discriminantal arrangements. So for fixed dimension K, the number of bounded regions of this discriminantal arrangement of this deletion map fiber is a polynomial in M of degree K-1 squared. So for K equals 3, it's this polynomial, which was stated and proved in the paper by Freddy and collaborators. For K equals 4, we have this polynomial of degree 9, which also appeared in the paper. And then, we can go further, right? So here the degree is 9, 16, 25, 36. So we proved this using work in combinatorics by Kozumi and collaborators. So this completely characterizes the Euler characteristic of the fibers. But the point I want to make here is that this really becomes visible in the tropical MLE with these particular Mandelstam invariants. Last slide, 1 minute to go. From soft limits to hard facts. So we're very, very happy. We verified Thomas Lamb's number for 3,9. So there's 74 million and so on, thousand solutions. This number decomposes in this way. So these are the regular solutions, so tropical MLE 0. This corresponds to codimension 1 strata in the fibration, codimension 2 strata. And this was done by solving the likelihood equation for all subproblems representing singular solutions. Massive numerical computations and lots of combinatorial bookkeeping, in my mind, a blueprint for the future of tropical MLE. We're working on 4.8. The current best guess is 5,211,769. We're very confident that we can complete this and that the final answer will be certified. Homotopy continuation will produce an interval arithmetic proof. And moreover, by computing all solutions and applying the from N to T happiness, we hope to prove the CUY conjecture on the 7 types of special configurations that arise in this problem. So conclusion, what is my goal of being involved in this subject? I'm excited because the work in this community in particle physics guides me and my collaborators towards new computational paradigms, say for likelihood inference and algebraic statistics. And en route, there's some nice combinatorics and some nice algebraic geometry. So with that, I thank for your attention. Here are a couple pictures. So here's the paper about a picture on special configurations from Freddy's paper. Second line is about statistics. Here's combinatorics, homotopy continuation. And last but not least is the inverse question of interest to physics.
Thank you, Bernd. Let's thank Bernd for his talk. Do we have some questions? So if you want to ask a question, please unmute yourself or raise your hand and then ask your question.
Bernd, great talk. I was wondering about these tropical critical points. Do I understand correctly that you an equivalent way to say it is you tropicalize the scattering equations, and you take, there's a tropical ideal for that, and you compute the solutions of that?
The short answer is yes, but for me, for me, these are not tropical. I solve the classical equations, but over a larger field. And I interpret the solutions tropically, right? So I think about this. So earlier, somebody was talking about the interactions with Grisham-Kalkin. So my perspective is a little bit different, right? So I solve the equations classically. I think about the classical solution over a larger field, and then I interpret those solutions tropically by passing through the valuation. So that's the longer answer, but the short answer to your question is yes.
I see. And another question is, these models that are important in amplitudes, a lot of them have some relation to Grassmannian, and that's sort of related to the symmetry groups, for example, PGL2 in the string amplitudes case, and SL4, for example, for the CEGM models, the Grassmannian is important because SL4 is comes up as a symmetry group, complexified symmetry group for space-time. So do you see such symmetry groups in statistics? Are they relevant?
I think less so in discrete, not so much in discrete models. In Gaussian models, in continuous distributions, Gaussians, you see a lot of interesting groups, Lie groups, Jordan algebras, you see quite a bit of this. Not so much in the discrete case that I described here. So for me, this was kind of interesting. So I have to confess, I thought about the Grassmannian before. So we started this, I did some likelihood calculations with the Grassmannian, and I computed some numbers, but I did it in this setting. So I looked at the Grassmannian, just the open Grassmannian in this sense. So I took M and I got completely different numbers. And at that time, the idea of passing to the moduli space simply didn't occur to me. So I would say nice objects in geometry, also with symmetry, probably could be useful for statistics, but they're not used a lot. But for me, it was eye-opening to see the passage from the Grassmannian to the moduli space. This I had not seen before. So yeah, anyway.
So this CEGM model, it doesn't have a particular interpretation in statistics.
No, this was really a new.
It's a new kind of.
Yeah, it was a new. This was really new, and of course, with hindsight, maybe there is one, but no, this had not been occurred in statistics.
Thank you.
Do we have more questions? I have one question. So these models are also related to the positive tropical Grassmannian and to cluster algebras. The last examples which you explained here is 3, 3,9 and 4,8. Is there anything special about these models? Because if you look at them from the point of view of like cluster algebra, there is something special about these models because there are not finite types anymore. Is there some qualitative thing here?
I think probably Thomas can chime in on this. I think what we observe when we study Grassmannians and matroid stratifications, these tend to be the boundary cases. You know, beyond 3, 9, 4, 8, somehow all hell breaks loose. And I think same with the cluster structure, things get just much more complicated. So I would just say, in some sense, one cannot hope for a general solution for any K and M, but we can push as far as we can. But now the cluster structure, I do not know whether how relevant it really is here in this case, because we really need the Euler characteristic of the whole complex thing. So I think just looking at the positive part may not be enough information for these cases, but maybe I'll pass it to Thomas. Maybe you have more insight on this.
I think it's still kind of a mystery that the non-realizable matroids appear just when the infinite type cluster algebras appear. It's exactly at the boundary that the finite type cluster algebras are the one where all the matroids are realizable. Yeah, but that's still a mystery. And so anyway, from different perspectives, the difficulty is at the same, at the same place. And also, also in amplitudes, G48 is one of the sort of places that we're studying very hard.
But is the problem really, it's a technical problem that it's too many of the solutions, or it's some more conceptual problem that there's some new type of behavior appearing at 3,9, 4,8, and then beyond?
My answer is there's new type of behavior. So what happens is that, I mean, there are different ways to look at it, but one thing is that the complexity of the singular solution, the special fibers, they just become very, very complicated. Right? So what happens if you look at this forgetful, and you see this in many settings. So this sometimes in matroid theory is called extension spaces or integration space. So the complexity of this map just increases dramatically at these boundary cases, and we see it here too.
You see, it's probably even worse beyond these cases where, like on the cluster algebra, that are not even finite type. Right?
Yeah, I mean, the advantage of the cluster algebra perspective is that it zooms in on the positive part, right? So the whole idea of positive Grassmannians and cluster algebras focusing is it sort of does away with the difficult part. So all the difficulty in the matroid stratification is away from that part. But the positive part is sort of a happy part. Mm-hmm. So in some sense, that's the right thing to do. You want to look at those parts of the Grassmannian and the matroid stratification that are amenable. And that's what the positive Grassmannian, the cluster structure does.
Thank you.